I'll go and give it to you now, David. Here you go. Yeah. So, actually, I have another one, so I'll go and give it. Huh? Okay, I only bring two, so you have to wait till they're done. Sorry. There you go. Kyle. Right. Okay. And it's Danae, right? Danae? Benet. Benet. Yeah. So when they're done, it'll just pass it off to you. If you're willing to wait, that's okay. But just hand it to me, and then I'll give it to her. Okay, Rich? Thank you. I think that you guys might be able to do the test without a calculator. But you're welcome. Huh? Oh yeah, there might be some square roots. Yeah. Okay. But try to do all the problems that require a calculator first. All right, guys. Have any big plans this weekend? It's almost Friday. It is. Today is Thursday. Tomorrow is Friday. I mean, for y'all, it's basically is Friday, right? Because this is your last class. Or you have more classes, I guess. Any big plans, though? No, we're doing Science Olympiad. Is anybody working that this weekend? Science? Are you doing Science Olympiad? Maybe. Okay. Yeah. Sorry, I'm not doing that for this class. So this, I think we're doing this maglev event where the students have to build a magnetically levitated train. Like this is a pretty cool thing actually, right? They build these trains, these real trains, and they ride on magnetic rails. So they don't actually touch the rails. They're levitated above the rails. And you do that because it eliminates the friction that's involved in trains because you lose a lot of energy to friction as it's rolling down the tracks. So these magnetically levitated trains have zero friction because they don't touch anything. But the students are going to build them. Are there any questions? We're going to do the exam about 30 minutes before the end of class. I think that'll give you plenty of time. But are there any questions about chapters 3 or 4? I think it's pretty straightforward, pulled heavily from the homework, like I said, from the basic knowledge things that we went over, the definitions of various things, the examples that we did in class. So if you've done those things, you should be well prepared, I think. Any questions? All right, guys. Well, I had told y'all that we were going to get into torques and circular motion, and so we're not going to do that. So if you feel offended or whatever, then you can take it up with my dean or my department head. But there's some really cool stuff in thermal physics that we're going to do that I think is applicable to a lot of what y'all do. So we're going to move on into thermal physics and the states of matter. Some of this you've probably seen, and if you've had chemistry, I think Faith, you're the one. Has anybody else had chemistry? Or physical science? Yeah, y'all had chemistry. Physical science, too, you would have covered this. So hopefully some of this is reviewed for you, but some of it might be new to you. Your book also offers a pretty good treatment of thermal physics and how it applies. A variety of realms. It's called Temperature and Heat chapter. Temperature is just a measure of whether something is hot or cold. In particular, it's a measure of the amount of thermal energy in an object. Y'all remember what that thermal energy, what it's related to? Like if we were to describe thermal energy on a microscopic level, how would we describe thermal energy? This was from chapter 4, I think. What's that? Right, the atoms are all moving around, and they have a certain amount of kinetic energy just because they're moving. And then that's a measure of the thermal energy. So when we measure the temperature of something, we're saying, well, how quickly are these things moving around? How quickly are these atoms moving? So temperature, or the thermal energy, is related to the kinetic energy of the particles. And that's chapter 4, but let me just write that. Thermal energy is proportional to, this symbol just means proportional to, the kinetic energy of microscopic particles. Of the atoms, I'll say. All right, atoms are the smallest unit of an element. And of course, they're made of protons, electrons, and what else? Y'all know this, right? Neutrons, right? And the neutrons. And so we'll look a little bit as we go through thermal energy at sort of the what's going on the atomic level or the molecular level. Now, when you group certain atoms together, then you make molecules. So molecules are just collections of atoms that are combined. Molecules are collections of atoms. So for example, ammonia looks like this. The molecule of ammonia is NH3. That means that there's one nitrogen atom and 3 hydrogen atoms. So if I were to draw this, it would look something like this. I'd have a nitrogen atom up here with 3 hydrogen atoms. And that's ammonia, NH3. A nitrogen and 3 hydrogen atoms. So molecule is just a collection of atoms. Now, when we talk about matter, matter is made up of atoms and molecules. There are phases of matter. There are 4 phases. Typically, we only know of 3, the phases of matter. I have a little clip I want to show you. You know, they might be giants. You know, they might be giants, the band. All right, they have a series of videos that I think are pretty good. Phases of matter. Let me write this first, though. We have solids. No, I'll go and play it, and then I'll write it. It's kind of fun. Come away from this, come back to it. Oh, shoot. Okay. So y'all know what solids, liquids, and gases are. No doubt you had this in high school, but let me just review it. Solids are rigid and retain their shape. Because the molecules or atoms are tightly bound. So within a solid, I'll have these atoms that consist of, you know, protons, electrons, and neutrons, and they're going to be bound together by forces. We often think of them as springs. And it just means that those are very tightly bound. They're not going to move with relation to one another. They're just going to be locked into place. So that what gives us solids, ice, wood, you know, solid objects. The next phase of matter is liquid. And in a liquid, the particles are freer, or the molecules are freer. To move, but they still stay within a certain distance of one another. So for example, if I have my particles, this particle can move around in different directions, and there are going to be other particles that will move around as well, but they're still going to stay at a sort of a fixed distance from one another. But they're able to move, but they still stay relatively close to one another. They're just not locked into this rigid framework that the solids are locked into. And then the final, of course, is gas. And gases, the particles are very separated. Molecules are really far apart. They're farther apart and are not bound to one another at all. In fact, we might not even consider that they touch at all. So you're going to have these particles, and they'll be traveling in all different directions, but they're not going to touch one another. They'll be really far apart and not really interact with one another. So they'll just sort of move around in random directions. Now there's a fourth state of matter. Usually we just talk about solids, liquids, and gases, but there's a fourth state of matter called the plasma, and the plasma consists of a highly ionized gas, a completely ionized gas. Usually these are really high temperatures, but not necessarily. Like for example, you ever seen the ball with the little orb floating in the middle? You know what I'm talking about? Like they have it at novelty shops where you put your finger on it and you get that arc that comes up. That's a plasma. And that's due to electrical voltages, and that electricity will actually ionize the air. What does it mean to ionize something? Right, you strip all of the electrons off. So in particular, what I'm talking about now is means that the protons and the electrons become separate from one another. So in a completely ionized gas, instead of having our protons with our electrons going around them, I'm going to have my protons, not this, but I'll have my protons, and then I'll have my electrons, and they'll all be separated from one another. So those electrons are completely stripped away from the atoms in a completely ionized gas. Another really common place that you find a plasma, anybody know where? On the sun. All right, the sun is really hot, and it's so hot that it just strips those electrons right off of the atoms, the hydrogen and the helium atoms. They Might be Giants had another song. Can I show this one to you? Is that okay? All right. Just say yes. That's the right answer. All right, so you need to know what are the four phases of matter and sort of how we define them: solids, liquids, and gases. Solids, the atoms are tightly bound to one another. Liquids, the atoms are still bound to one another, but they're able to freely move about. And then with gases, the particles basically don't interact at all, and they just move in all different directions. And then the plasma is just a highly ionized gas, or even a completely ionized gas. All right? Y'all probably know those, but you'll need to know them for the next quiz as well. The four stages of matter, or the four phases of matter. We also need to know what are the three different temperature scales and how they're defined and how to convert from one to the other. Now, I'll provide you with the equations to do this, so no need to memorize that, but you need to know how to use them. And there are some homework questions to do that. We use several different temperature scales. The most common that we use is the Fahrenheit scale. You might know what Fahrenheit means? It's German, right? You might take German. What Fahren means, or height. What do you think height means? it means heat. Fahrenheit, the height means heat. And if I forget my German, but I'm pretty sure that Fahren means to drive, like you drive heat, to drive heat. All right, so we have 3 temperature scales, the Fahrenheit, the Celsius scale, and the Kelvin scale. Like I said, you'll need to know what these are defined on, what they're based on, and then also how to convert from one to the other. The conversions are easy. As I said, I'll provide that in the the equation sheet. Fahrenheit is most commonly used in the U.S. In fact, the U.S. is really the only country that uses the Fahrenheit scale. Most commonly used in the U.S. It's defined by the melting and freezing point of water. And for the melting point, that's 32 degrees Fahrenheit. Or excuse me, not the melting and freezing point, the boiling and freezing points of water. Sorry. Let me rewrite that. The boiling and freezing points of water. So the freezing point, the point at which it freezes, is 32 degrees Fahrenheit, and then the boiling point of water is 212 degrees Fahrenheit. All right, so there are these particular places where water freezes, a particular temperature, and the Fahrenheit scale says we're going to call that 32 degrees Fahrenheit. And then there's a particular temperature where water boils, and the Fahrenheit scale says, okay, we're going to call that 212 degrees Fahrenheit. And based on that difference between those two temperatures, then we have the scale for the size of the degree. All right, so if I were to put this on a thermometer, I have 32 degrees here for the freezing point of water, and then up here I have 212 degrees, and the size of the Fahrenheit degree is based on the difference between those two. All right? Now, the Celsius scale is very similar. It's also defined by the boiling and freezing points of water. It's most commonly used in Europe and other countries. It's also used a lot by scientists because it's an easier scale to use than the Fahrenheit scale, because instead of having these sort of random boiling and freezing points of water, it's based on 0 degrees and 100 degrees. So it's defined similarly by the boiling and freezing points of water. So the boiling point is 100 degrees Celsius, and the freezing point is 0 degrees Celsius. So on this same scale, this would be Fahrenheit over here. Over here, I would have Celsius scale, and down here I would have 0 degrees, and up here I would have 100 degrees Celsius. So 100 degrees Celsius is the same as 212 degrees Fahrenheit, and 0 degrees Celsius is the same as 32 degrees Fahrenheit. Now, when I talk about a degree Celsius, is that degree Celsius going to be bigger or smaller than a degree Fahrenheit? So say the temperature changed by 5 degrees Celsius. Is that a bigger change in temperature or a smaller change in temperature than 5 degrees Fahrenheit? In Celsius, it's bigger. So a degree Celsius is bigger than a degree Fahrenheit because it's from 0 to 100 to the boiling to the freezing, from the freezing to the boiling point in the Celsius scale, and it's 32 to 212 for the Fahrenheit scale. Let me write that in words. I'll just draw in here my degrees the size of my change in temperature is going to be bigger for a single degree Celsius. 1 degree Celsius is bigger than 1 degree Fahrenheit because there are fewer increments between the freezing and boiling points of water. All right, so that's the Fahrenheit and the Celsius scale. You can convert between these two. These are in your book, and they'll be on your equation sheet. Can I go down from here? So you might expect a question on the test, just converting either Fahrenheit to Celsius or vice versa. All right, the temperature in degrees Fahrenheit is equal to 9/5. The temperature in degrees Celsius plus 32. So for example, if I have my temperature in degrees Celsius is equal to 5 degrees Celsius, then I can find the temperature in degree Fahrenheit is going to be 9/5 times 5 plus 32. And so that's going to be 32 plus 9, which is 41 degrees. That's going to be 41 degrees Fahrenheit. So 5 degrees Celsius equals 41 degrees Fahrenheit. Similarly, I can convert from degrees Celsius to degree Fahrenheit. So the temperature in degrees Celsius is going to be 5/9 times the temperature in degrees Fahrenheit minus 32. So for example, if the temperature in Fahrenheit is equal to 50 degrees Fahrenheit, then I can find the temperature in degrees Celsius is going to be 5/9 times 50 minus 32, and that's equal to 10 degrees Celsius. All right, so I can say then that 50 degrees Fahrenheit is equal to 10 degrees Celsius. So you should be able to convert back and forth between those, all right? Like I said, I'll provide you with the equation, so it's really just a matter of knowing how to plug in the numbers and use them in that way. Is that clear on how to do that? Yeah? All right. Do you have any idea what room temperature is in Celsius? This is sort of a good number to know. No, it's 32 is pretty hot. It's more around 20 or 25 degrees Celsius. All right. So room temperature is about 20 to 25 degrees Celsius. Neither one of these is the SI unit. The SI unit for temperature that we use is the Kelvin, named after Lord Kelvin. We won't use it so much in this class, but you do need to know that it exists and what it's based on, because it is the SI unit for temperature. It's the Kelvin. It's abbreviated as a capital K. So we don't use it very often, but scientists use it. But usually when you're dealing with the body, you use those other temperatures. The Kelvin temperature is based on something different. The standard is based on the absolute zero temperature. Absolute zero is the point when all random motions in a material stop. It is the lowest temperature that you can achieve because, and it's also not really achievable because you can't stop those atoms from vibrating. So the vibrating atoms in any material just lend an intrinsic temperature to that material because they have kinetic energy associated with them. So we can get pretty darn close. Like with liquid helium, you can get down to millikelvins, so hundredths or thousandths or even millionths of a Kelvin, but you can't really achieve absolute zero. So it's based on the absolute zero temperature. It's also based on the triple point of water, because remember you need two different things to establish a scale. It's also based on the triple point of water. This is a particular temperature and pressure. Temperature and pressure when water exists as all three phases. Exists as a solid, liquid, and a gas. All right, so it's based on the absolute zero temperature, and then it's based on this triple point of water. I forget what exactly that temperature is. It's right around 0 degrees. All right, now to convert from Kelvin to Celsius, you're going to use this. May I go down from here to the next page? Give y'all just a second. All right, so to convert from Kelvin to Celsius, you'll use this expression. That is that the temperature in Kelvin is equal to the temperature in degrees Celsius plus 273.15. And so 0 degrees Celsius, for example, is going to equal 273.15 Kelvin. All right. For example, absolute zero which is 0 Kelvin, remember that's the lowest temperature that you can go to, is going to equal negative 273.15 degrees Celsius. So it's pretty darn cold, negative 273.15. All right. So we got, I forgot to bring a file. Can y'all give me just a second to pull it up? I can have it in like 1 minute. I use SkyDrive. Do y'all use SkyDrive? It allows you to access your computer from any other computer, and you can pull files off of it. It's really pretty cool, but I have to do this. Just give me just a second. We're going to move into linear expansion. I have a cool clip from